Comparative study on seismic behavior of composite and RCC plan irregular structures. Abstract: this paper investigates comparison of a composite structure with concrete-filled steel tubular columns, a composite structure with concrete encased dissection columns and a RCC structure. All the models considered are G+15 story and are irregular in plan, and the irregularity condition as per IS 1893 to 2002 is satisfied, resulting in T-shape and plus-shape models. It was observed after performing response spectrum analysis on the models that the stiffness is less in composite structures when compared to RCC structures. The displacements and drifts are less in RCC structures owing to larger value of stiffness but are within the permissible limits. The base shear and base moments are found to be less in composite structures due to the fact that the dead weight of composite structures is less compared to RCC structures. There is no significant difference in the response parameters of the two composite structures. Keywords: concrete encased dissection column, concrete filled steel tabular column, RCC, response spectrum analysis. Introduction. As the population in the world is increasing at a faster rate, the need for buildings are also going hand in hand. As some of the countries are short in terms of area, the need for taller buildings becomes essential in the society. Composite construction is formed when two heterogeneous materials are bonded together as a single element. The composite structures such as steel encased with concrete are economical, time and cost efficient in major civil structures such as bridges and high-rise building. In past, for the design of buildings, the choice was between a concrete structure or masonry structure. With the failure of these structures due to earthquakes forced the structural engineers to find an alternative method of construction. Many structural engineers in India are not welcoming the use of steel concrete composite buildings because of its unfamiliarity, lack of awareness, and its analysis and design seems to be little complex. From the literature available in this area, it can be said if properly configured, then composite steel concrete system will provide extremely economical structural systems with speedy construction, high durability, and high seismic performance characteristics. 2. Literature review. Vamshi Krishna, S.V. Surindar. 1. Presented a paper showing the comparison of seismic analysis of RCC and composite 18-story building. The results show that some parameters such as time periods and story displacements were higher in composite, and story forces, bending moment and shear forces were less in composite structures. Sachin S2 presented a paper on the seismic behavior of 15-story irregular building through dynamic analysis as per IS 1893:2002 for seismic zone 4 and soil type medium. The results were compared for various parameters like time periods, frequency, story drifts and story displacement. CFST columns were compared with the CEC columns. Sohail Sheikh III conducted a study on behavior of concrete encased columns in irregular buildings under seismic conditions. A detailed analysis of multi-story G+20 building having various irregularities with concrete encased columns has been carried out against RCC columns in mass and stiffness irregularity. Base shear was found to be reduced in concrete encased columns in both the irregularities. The time periods and the displacements were found to be higher in composite structure when compared with the RCC structure. He concluded that concrete encased columns are suitable for stiffness irregularity building due to its high stiffness property, which enables the structure to resist. Vishwanath SN4 presented a paper on seismic analysis of multi-story RCC and composite buildings subjected to vertical irregularity. The study is carried out on the comparison of RCC with composite structure for G+16 buildings situated in seismic zone 5. The models consist of rectangular, mass irregularity, stiffness irregularity and geometrical irregularity, and the composite beams are provided without shear connectors. The result parameters which are compared were base shear, story displacement, and story drifts. Mohammed Sabath K5 presented a paper on behavior of seismic analysis of irregular composite structures with shear connectors. The study is carried out on plan irregular structure of medium-rise building of 10-story building. Modeling and analysis done to estimate the behavior of shear connector and is compared with the RCC structure. It was found that story displacement is higher in composite structure. The composite structure has reduced stiffness to make the structure flexible. Storey drifts are large in composite structure than RCC. Axial forces are reduced by nearly 50% margin in composite structures. Rajendra R. Pawar, Vinay Campbell 6 presented a paper of comparison of composite and RCC buildings. 2G plus 15 residential buildings of composite and RCC structure are analyzed and designed using A-tabs with different story heights of 3m and 4m. It is found that the depth of beams in composite structure is less than RCC structure, which results to also reduce the sizes of columns in composite structure. The design of smaller sections for same loading in beams and columns. For same structure, when the floor height is increased, it is found that it doesn't make big changes to axial forces and bending moments. This study aims to compare the response parameters like displacements, drifts, stiffness, shear, moments and axial forces of G plus 15 story plan irregular composite structure with concrete encased columns, plan irregular composite structure with concrete filled columns and conventional RCC structure models located in seismic zone 5. 3. Methodology. A. Elements of composite construction. A steel concrete sectional composite beam is fabricated with the help of a steel beam sandwiched over a reinforced concrete slab is cast by using an element called shear connectors. Shear connectors improve the load carrying capacity of the element/member and overall rigidity in steel concrete composite beam. The two primary functions of shear connectors are, a. At the interface of beam and slab, this transmits the shear acting along longitudinal, and b. Helps in avoiding the steel beam and concrete slab splitting at the interface/junction. The overall depth of the beam is decreased by the action between steel beam and concrete slab. A metal deck sheeting is provided on beam and with the help of shear connectors the deck sheeting and the beam are connected. Then the concreting is done over the deck sheeting. Figure 1 shows the composite deck slab. A column is considered as a compression member. Concrete encased I-section, concrete filled steel tubular, CFST, are used in this paper. These both are designed using AISC 360-10 codebook. Figure 2 indicates a concrete encased column and Figure 3 shows CFST. B. Building models used in the study. The study is carried out on for the behavior of G plus 15 storied building of T and plus shaped models. The T-shaped RCC model is labeled as RCT15, composite structure with concrete encased I-section columns as NT15 and composite structure with concrete filled steel tubular columns as Phi-T15. Similarly, the plus-shaped models are labeled as RCP15, NP15, and Phi-P15 respectively. The geometric details of the building models are as shown in Table I. The loading details and the seismic parameters are shown in Tables 2 and 3. The models were analyzed in A-tabs software. All the sections were designed as per codal requirements. The RCC model was designed using IS codes and the composite models were designed as per AISC 360-10 due to unavailability of Indian code for composite structures. Fig 4 and 5 represent the plan and 3D view of T-shaped models. Fig 6 and 7 represent the plan and 3D view of plus-shaped models. The time period of all the models considered is shown in Tables 4 and V. As the time period reduces, the stiffness of the building increases because time period is inversely proportional to the stiffness of the building. B. Story displacements. Story displacements of the T-shaped models are shown in Fig 8 and 9. It can be seen that the top story displacement for the model NT15 is almost twice compared to RCT15 and for the model Phi-T15, the displacement is about 60 to 70% more when compared to RCT15. Fig 10 and 11 show that the maximum displacement for the models NP15 and Phi-P15 is about 85 to 100% more when compared to the model RCP15. When the two composite structures are compared, it can be seen that the difference is very less. See story drifts. The graphs in Fig 12 and 13 shows that the story drift for composite structure, whether it is of T-shape or plus shape, is comparatively higher than RCC structure in both transverse and longitudinal direction. The drifts in the composite models were about 80 to 100% more when compared to the RCC models. D. Story stiffness. Fig 16 to 19 show the stiffness of the models. It can be seen from the figure that the stiffness of the composite buildings is less than half when compared to the stiffness of the RCC buildings. Because of inherent ductility characteristics, steel concrete composite structures have less stiffness compared to R.C.C structures, leading to better performance in the event of an earthquake. Base shear. Fig 20. Base shear of all the models. Base shear is the horizontal reaction to the lateral forces, and horizontal forces results from the story weight. In RCC models the self-weight is more, and hence resulting in the highest value of base shear. It can be seen from the Fig 20 that the base shear for the models NT15 and Phi-T15 in X direction is about 60% less when compared to the model RCT15. In Y direction, the base shear for NT15 and Phi-T15 is about 50% less when compared to RCT15. The base shear in the models NP15 and Phi-P15 when compared to RCP15 is about 56% less X direction and 45% in Y direction. Overturning moments. From Fig 21 it can be seen that the RCC has got more overturning moment than the composite structures. This is due to the lateral forces. The overturning moment in the models NT15 and Phi-T15 is 66% and 54% less when compared to RCT15 in X and Y directions respectively. For NP15 and Phi-P15 the overturning moment is 61% and 46% less in X and Y directions when compared to RCP15. Axial forces. Fig 22 shows the axial forces for some of the columns of T-shaped buildings. The columns C6 and C9 are corner columns, C11, C15 and C17 are edge columns, Fig 4. Fig 23 shows the axial forces for columns of plus-shaped buildings. The columns C2 and C9 are corner columns, C15 and C19 are interior columns and C17 is an edge column, Fig 6. It can be seen that the axial forces in the composite structures are less compared to RCC structure. The columns at the reentrant corner, C9, has higher value of axial load. It can be clearly seen that internal columns experience higher forces than the external ones. Conclusions. The following conclusions are drawn from the analysis done on the models. The displacements in the composite structures are more when compared to RCC structures, but within the limit of the IJERT provisions. The story stiffness in composite structures in nearly half compared to RCC, thereby increasing the ductility of the structure. The base shear and base moments are also very less compared to RCC structure. This could be due to the fact that the dead weight of RCC is more compared to composite structure. When the two composite structures were compared, it was found that there is no significant difference in the response parameters of the structure with concrete filled steel tubular columns and with concrete encased I-section columns.